right? 109. 8109. How many unpaired electrons will be found in the ground state of magnesium? Well, we see magnesium is filling the 3s orbital, and there's one electron, one up and one down, so there's none there. No unpaired electrons in magnesium. Phosphorus. Phosphorus, we see we're filling the 2p orbital, and we have 3 electrons there, so we have 3 unpaired orbitals. This is for magnesium. This is the 2p for phosphorus. What's next? Vanadium. Oops. Vanadium. So we have the d orbital, it's the 3d, and the m sub l values for 3 are negative, or yes, for l equals 3, -3, -2, -1. No, let's see, what is this? D is 2, sorry, L sub L for is 2, so it's -2, -1, 0, 1, and 2. And for vanadium, we just have 3 electrons, 1, 2, 3, so that would be 3 unpaired electrons in vanadium. All right, 8, 11, right? The shorthand electron configuration for the following compounds. The shorthand electron configuration. Well, the shorthand one means we just use the noble gas configuration where we can. So for nickel, we look at nickel, and we go back to the first noble gas, which is argon. So then we just say argon as the noble gas core. Then we have potassium and calcium, that's 4s2. So this is for nickel, the electron configuration of nickel. Argon, 4s2, 3d8. Right, because we count across in the 3d shell here from scandium, 1, 2, 3, 4, 5, 6, 7, 8 to nickel, that's 8, right? So that's for nickel. We're on 811. Cesium. For cesium, we go back one and it goes to xenon. Cesium, xenon. And then after xenon, we're filling up our 6C, or 6S, 1. All right, there's just 1 electron. Cesium is number 55, the first electron in the 6th column. And that's this S block. Okay, cesium, germanium. So germanium, argon is our shell again. 4s2, 3d10, 4p2. Right, going gallium and then germanium. Okay. Bromine. Argon is our core. Electron configuration using the noble gas shell, or noble gas core. Argon, 4s2, that's potassium and calcium. 3d10, that's scandium to zinc. We're going to bromine, so then we have 4p5. And that is gallium to bromine. All right, and then bismuth. Bismuth. Okay, so bismuth's a little bit complicated here because you go back to, well, you go back to the noble gas core and it's xenon, right? So that's not the complicated part. The complicated part is after xenon, we go to cesium and barium, that's 6s2. And then we have to see that we go lanthanum 57 to 71, so that's 4f let's see, 14, wait, 4f14 to lutetium, and then hafnium to mercury is 3, 4, 5 d9. Hafnium to mercury. And then we go 6p3. 6p3, and that is the bismuth. All right? So the thing that you have to remember there is that at lanthanide, you actually go down to the inner transition metals, and you can't forget to count those inner transition metals. So let's double check that one. 811. Whoops, 5D, not 9, 5D10. Sorry about that. 5D10, 6P3, is that right? Bismuth, 5D10, 6S2. Oh, did I not? And I also forgot the 6. No, I got 6S2 here. 4F14, 3D10. Where are we at? 4F14, 5D10, 6S2, and 6B3. Okay, that's right. Yeah, so the answer in the back of the book has these in a different order. And it doesn't matter the order that you put those. It's nice to keep the 6s with the 6s, but we filled them the way that they were be filled here. But afterward, it doesn't matter the order. So just as long as you remember that you have 6s here. Just as long as you can look at it and see, here's the 6s, here's the 4s, and here's the 5s. Don't get tricked into thinking, oh, there's only 3 6s, right? Okay, so 813. Draw a complete orbital diagram for magnesium and titanium. Orbital diagram for magnesium. So our orbital diagram shows energy levels right here, and we're just trying to identify where all the electrons are in magnesium. Okay? It helps to identify the electron configuration: 1s2, 2s2, 2p6, 3s2. So there's our electron configuration, and then we can draw this orbital diagram showing the electrons' energy levels increasing as we draw them up to from the bottom to the top. So we can draw lines, we can draw circles. We'll just draw lines to make them less confusing. This is our 1s2. Here is our 2s2. Here will be our 2p6. All right, the 2p6, the 2p is divided into 3 because L equals 1 for the p value. So m sub L can be equal to -1, 0, or +1. And then we have our 3s2. And the electrons look like this, right? The electron going up. And this is how we fill them. And magnesium has 2 in the 3s2. This is the 2p. You don't have to put on the orbital diagram the 2 with the 1s2 because you can see how many electrons there are, right? And they're not always necessarily going to be filled. All right, so there's our electron configuration for magnesium. And now we're going to do titanium. Titanium, right? Or is it thallium? Titanium. So that is element 22. So we can pick up here with 3s2 from magnesium, 3p6 from aluminum to argon, 4s2 potassium to calcium, and then 3d2 from scandium to titanium. All right, so we have our 1s2, our 2s2, 2p, 3s, 3p, 4s, and then the next one filled is our 3d. All right, this is full, this is full, this one is full, this one is full, this one is full, this one is full, and then the 3d has only 2 electrons in it. All right, so that is the orbital diagram for titanium. 815, draw the orbital diagrams for the shorthand configuration of nickel, cesium, germanium, and bromine. 815. Okay. So they basically want us to do the same thing, but looking at the shorthand for 815, nickel, we just start off with our argon, and then we can go right from there to our 4s2 and then our 3d8. So here's our 4s2, or 4s, that we showed has 2 electrons, and then our 3d8. 1, 2, 3, 4, 5, 6, 7, 8. All right? So that's for nickel. Cesium. Correct? Wait, we're on 815 now. Cesium, we have xenon, and then we're just going to have a 6. So this is xenon, and then this is going to be 6s, and there's going to be just 1 electron there. That's for cesium. Germanium. This is going to be argon. This is going to be a 4s. After argon, germanium, 3d, and then a 4p. So 3d, and then a 4p. All right, this is full. This one here is full. And germanium has just 2 electrons in that 4p. So this is our 4p, this is our 3d. Right? Okay. Excellent. Germanium and now bromine. Bromine. Erase this down here. The electron, it was still argon. We're going then 4s, 3d10, 4p. So we just did germanium, so bromine just has 1, 2, 3 more electrons. So 1, 2, 3 more electrons. So there's just 1 electron unpaired. All right. That's the end of 815. 817. What is the value of N for the valence shell of tin, potassium, bromine, and bismuth? Well, the N value is equal to the column that they're in. So the N value for tin is, or so the row, it's in the 5th row, so N equals 5. N value for potassium, 4. N value for bromine, also 4. And N value for antimony is 5. So 5, 4, 4, 5. 817. Let's see if we're missing something there. 817, 5, 4, 4. Uh-oh, we missed. What was that one? 8, 117. Bromine was 4. Oh, I misread it. I went down to 818. 817, they're not looking for antimony, they're looking for bismuth. And for bismuth, you can see that it's on the 6th row. So the answer is 6 for the N value of bismuth. All right, 819. I skipped down to 818 on accident. 819. Give the configuration of the valence shell. Give the configuration for the valence shell of sodium, aluminum, germanium, and phosphorus. 819. Valence shell for sodium. So sodium's valence shell, that means the outer shell, we look at sodium, and all of its valence shell is where N is the highest value, right? So if we look at the electron configuration really quick for sodium, 1s2, 2s2, 2p6, 3s1, right? So this is the electron configuration for sodium. And the ones that have the highest N value, which is this 3 here, those are our electronic configurations. So the electron configuration of the valence shell for sodium would just be 3s1. All right, do they want an orbital diagram with that too? No, just that. Okay. So for aluminum, where's aluminum? We have electron configuration of 1s2, 2s2, 3p or 2p6, 3s2. This is for aluminum now. 3d1. So the electron configuration for aluminum is here, and the electron configuration for just the valence shell would be that much right there. Okay? Because, again, the valence electrons are the one with the highest values. Okay? All right. 8. So sodium, aluminum, 8. Wait. Did I miss one? Oh, that's right. 819. Sodium, aluminum. Now, germanium and phosphorus. So germanium. Germanium's electron configuration. Germanium. Electron configuration. 3s2, 3d6. Let's erase this commercial circle here. So the electron configuration for germanium is as follows. 3d6, 4s2, 3d10, 4p2. All right? So that's the electron configuration for germanium. And the highest n values, which in this case are 4, those are our electron, or our valence shell configuration. So the 3d10 is not included because it's not the highest n value. So we would just have our, oh wait. Yeah, germanium. So that was 819. Let's double check that. Germanium, 4s2, 4p2. Yeah. So phosphorus, last one, we stop at 3p3. So this would be the electron configuration for the valence shell of phosphorus. Okay. Let me double check the time here. Okay. All right, so 8:19. 8:21. Draw the orbital diagram for the valence shell of So we're drawing the orbital diagram for the valence shell of those same ones. So for sodium, our S value is just going to be 3s. We're going to have 1 electron, right? So that's an orbital diagram. Energy coming up here. Here's our 3s, and we have 1 electron. For aluminum, it was 3s2, 3p1. So that's the orbital diagram for our aluminum. For germanium, we had 4s2, 4p2. That's for germanium. For phosphorus, 3s2, 3p3. All right. Okay, 121. 123. Okay. 123. If the core electrons were 100% effective at shielding the valence electrons from the nuclear charge, and the valence electrons provided no shielding from each other, what would be the effective nuclear charge felt by the valence electrons in sodium, sulfur, and chlorine?